Hi and welcome to this Leaving Cert Higher Level Applied Maths video. In this video, we're looking at the 2023 Higher Level Deferred paper, and we are looking at question 6, part A. And this is a uniform acceleration question. So motorbike B traveling at speed 5.5 meters per second and constant acceleration of 0.5 meters per second squared on a straight stretch of road is overtaken at a road sign S by car C traveling at speed 11 meters per second and a constant acceleration of 0.125 meters per second squared. Calculate the greatest distance the car C is ahead of motorbike B. So what we need to remember is the greatest distance between two bodies will always happen when their speeds are equal. Now that's a when, so that's getting us time. Be careful, this question is asking us for the actual greatest distance, but our first step is by getting that time. Now, and there's a little caveat to using that, and this will only happen where one has overtaken, so one body has overtaken the other, and then the overtake will happen again. Because obviously, if a car is ahead of another car and they're going faster and faster and faster, the whole time the gap will get bigger, bigger, bigger. So this is in a very specific circumstance where we've had an overtake. So like if you take a look here, the car overtakes the bike, and then what we'd expect to happen is the bike will then overtake the car. And the reason for that is because although the bike is going slower, it has a bigger acceleration, so it will eventually become faster. So the greatest distance will happen where their speeds are equal. So let's set up our little table. I have two bodies, so I'm setting up my VUAST for both of them, so B and for C. So we want to have where the velocity of B is equal to the velocity of C. We're going to use for velocity is equal to U plus AT. What that means for B is 5.5 plus 0.5 t. Where is that equal to? 11 plus 0.125 t. So what that gives us is a nice little equation that we can work with. Getting all the t's on one side, I get 0.375 t is equal to 5.5. So t is 5.5 divided by 0.375. So 5.5 divided by that, and we get 44 over 3 seconds. Or if you want to do some rounding, that works out as 44.6 recurring, so 44.7 seconds. Now, that's the time when the greatest distance happens. So what we need to understand is when the time is 44 over 3, what is the distance traveled by both? And it's going to be the difference in that. So because so C is ahead of B, that means SC is going to be bigger than SB. So we will find the greatest distance when SC take away SB, when they are at the same speed. So when time equals 44 over 3. And this is going to give us our greatest distance. So that is going to be, for this formula, we're going to use S equals UT plus a half AT squared. So just giving us some room to work. So SC, so we're going to have 11 times 44 over 3 plus a half A, which is 0.125, 44 over 3 squared minus the displacement of B, which is going to be 5.5 by 44 over 3 plus a half times 0.5, 44 over 3 squared. And we can go to our calculators to work that out. I'll give you some numbers though. So we have it 484 over 3 plus 121 over 9 minus 242 over 3 plus 484 over 9. And then that gives us final answer of 121 over 3 meters, which is equivalent to 40.3 recurring meters. So that's the greatest distance that C is ahead of motorbike B. So part 2 then says calculate the distance from S to the point where B overtakes C. So the car is overtaking the bike, and the car then gets a bit further away until it reaches that maximum distance, which we just worked out. Then the motorbike's going to start catching up on C until the point that actually it's going to overtake C again. So B will overtake C when they've traveled the same distance or displacement from that road sign S. So SB is equal to SC. Now we can't use our time or S's from the previous part. All we can go back to is our initial, our U, and our acceleration. So what we want to do here is we want to basically have the SB is equal to SC, and we're going to use the formula S is equal to UT plus a half AT squared. So what this is going to do, it's going to find when it happens. So for B, that's going to be 5.5T plus a half AT squared is equal to, for C, 11T plus a half AT squared. We're now going to be able to solve that to figure out our time, and then we're going to be able to use that time to get the distance. So keep an eye on the question, because sometimes we get so excited about the fact we know how to do this. So when the displacements are equal, we forget to answer the question. So what we have here is a quadratic. So let's get everything over to one side. So that gives me minus 0.1875 t squared. I've effectively brought everything to the right and then let that equal to 0. Highest common factor, 5.5 minus 0.1875 t equals 0. So the 2 times that will happen is t equals 0, but that's not valid for us. That's at the sign S. We knew that happened. And our other time is going to be 5.5 divided by 0.1875. And that's going to give me 88 over 3 seconds, or 29.3 seconds in decimal. So therefore, we need to go work it out. It actually doesn't matter which one we work with, because the distances should be the same. So I'm going to work out SB, and that's going to be 5.5. Remember, we've just worked out our time here as 88 over 3 seconds. So that's 88 over 3 plus a half a 0.5 t, 88 over 3 squared, and that can go to our calculators, and we get 3388 over 9 meters, or in decimal, that's about 376.4 meters. So using the axes below, sketch the shape of the displacement time graph where the displacement of B relative to S for the first 30 seconds of its motion after it passes S. Using the same axes, sketch the shape of the displacement time graph where the displacement of C relative to S for the same period of time. Include scales in your axes. So we are very comfortable with working with velocity time graphs, and in uniform acceleration, what that means for us is we get these lovely straight line graphs. However, when we deal with displacement, we need to think about what kind of shape that is. So we're going to end up with a curve for both of these. And if you're not comfortable with that, what we can do is we can use the information we have to see it. So here is a function of displacement with respect to time for B, the bike. And you can see here that we have a positive quadratic. And equally, when we do it for the car, we get the same. So we get 2 curves. Now, again, we know what a positive quadratic looks like, but you may be struggling to kind of think about, okay, but what does that mean for my graph? So we can use some substitution to help us, and I'll talk you through some things that I suppose we really need to see in terms of a sketch. So the first thing I'll do is, from part 2, we know that they meet when the time is about 29.3 and the distance is about 376.4. So let's put on our scale. So based on those numbers, I'm going to break my displacement up into 50s, and I'm going to break my time up into 5 seconds. What that means is I know that both of these pass each other when time is 0 and there's no displacement. Again, remember that's the displacement from the point of passing. So that is our first point. And then the second point is around 29.3 and 376.4, which is about there. So basically, these are where our two curves are going to be. So we're going to have to think about the fact that the car is ahead of the motorbike until the motorbike passes it again. That means when we draw our curve, we're expecting the bike curve to be below the curve for the car. And we also know that it has the maximum distance or greatest distance between them. It was about 14 point something, about 14.7 seconds. So I'm going to do a quick little table just to get a little bit of a sense of what's going on here. So in the table, we have our 0, our 10, and our 20. So 0 is not very exciting. We've already that on the diagram. So for 10, it gives me this for the bike, and it gives me this point for the bike after 20 seconds. So connecting those, I get this kind of curve. So it's a very subtle curve, but we are getting a curve. Now, what we're looking at is we're getting the car, and the car should be higher. So again, I'm going to use just these quick points just to get a sense of it. And they are my two versions, or well, the 2 points at the same time for the car, and I get this curve. Now, because we're looking over such a small distance, this looks nearly straight. And I know that, but that is part of a curve. The other thing I suppose we're really trying to see, apart from, I suppose, labels important, have we got a sense of a curve rather than these being straight lines? Have you got the car on top of or above the bike? And we're looking for this biggest gap at around 14.7 seconds. So it's there. I've just put in like a little purple arrow. So we're kind of seeing the biggest difference between my two graphs is there, which ties in with what we've worked out in part 1.